Today's lesson will be on factoring. It should be review from last year's math class, and the two kinds of factoring we're going to be talking about today are greatest common factor, abbreviated GCF, and difference of two squares, abbreviated as DOTS. When we do greatest common factor factoring, it is dependent on you being able to determine the greatest common factor. If by chance you are having difficulty determining the greatest common factor, please make sure that you take a look at our Google Classroom, because in Google Classroom there are some optional videos if you'd like to watch them to help you determine the greatest common factor. That's a previous skill that's needed in order to do the greatest common factor factoring. So when I look at question number 1, I recognize that I have two terms here, and the two terms are separated by a minus sign, and I'm looking to see what I can divide out of each of those terms, or what number or variable is a factor of each of those terms. So I'm going to go through part by part. When I first look at this, I see that I have a 5 and a 15, and the greatest common factor of 5 and 15 is going to be 5, so 5 is part of my GCF. I also know that when I look at the x's, this is x to the third and x to the second. So the most amount of x's I can divide out of each of those terms is x to the second. You're usually going to be taking the smallest exponent that you see. And then when I move over one more and I look at the y's that are there, I've got y to the first and y to the first, so I can take a y out of each of those terms. When I get to this point, I have now determined my GCF, and I'm going to have what I call some leftovers in the parentheses, which is going to be made up of the first term of the original problem divided by the GCF, and the second term of the original problem divided by the GCF. So I'm actually going in and I'm dividing them out. So when I look at the first term divided by the GCF, I have 5 divided by 5, which is 1. X to the third divided by x to the second, which is just x, and then y divided by y, they cancel out, and I could write a times 1 on there, but most of the time we don't write anything. And then I move on to the second term being divided by that GCF, which is right here. Negative 15 divided by 5 gives me negative 3. The x squared divided by x squared cancels, and y divided by y cancels. So the y's are going to cancel out as well as the x's, which means that what you see is going to be our final answer. The only thing that I would like to add in here is that in the final answer, when I go through to do this, sometimes I like to rewrite it in a little bit neater of a fashion. So this will be 5x squared y, parentheses, and I'm only writing x minus 3, not 1x minus 3. You could leave the 1 there if you wanted to. It's just that it's not necessary. When I go on to question number 2, I'm doing the same process. I'm determining with my now 3 terms what is a common factor and the greatest common factor of each. So when I look at the 12, the 20, and the 28, I know that 4 goes into all 3 of them evenly, or each of the 3 coefficients are evenly divisible by 4. And then when I look at the x's, I've got x to the third here, x to the second here, and x to the first here. The most amount of x's I can take out of each term is x to the first. I pick the lowest exponent that I see in the original problem. And then of course, just like the last problem, we are going to have some leftovers. And the leftovers is whatever I get when I divide each term of the original problem by the GCF that I just determined. So each term is getting divided by 4x, and I'm going to go in here now and divide each of the original terms by 4x. So for the first term, 12x to the third divided by 4x, 12 divided by 4 is 3, x to the third divided by x to the first is x to the second. When I move on to the next term, divided by 4x, I get 5x, and then the next term divided by 4x, when I do this, I get minus 7. The x's actually cancel here. So that becomes my final answer. Question number 3 is going to be done the same exact way. In question number 3, I'm looking at my two terms and I'm saying with respect to the 30 and the 6, the coefficients, they're both divisible by 6. Just trying to make a little more room here. And then I go in and I look at each of those two terms and I look at their x's. So there's an x to the third and an x to the second. The most I can take out of both of them is x to the second. And then I move along and I do the same thing with the y's, y to the third and y to the second. So the most amount of y's I can take out or divide by is y to the second. And then remember, we have this set of parentheses which contains our leftovers. It contains the quotient, or the answer to what I get when I divide the original problem's terms by that GCF. So when I go back to the first term and I divide it, I end up getting 5xy. The second term, when I divide it, this one's a little bit more interesting. You can see that you have 6 divided by 6, which is 1. X squared divided by x squared cancels, y squared divided by y squared cancels, and you basically just end up having the 1. Sometimes kids will forget to put that last term on there. Please remember that 6 divided by 6 gives you 1, not 0. So you do need to have that 1 in there. It's almost like a placeholder. When you're doing GCF factoring, one of the things I'd like to remind you of is that you are always able to check your answer by distributing. So in each of these final answers, you can see that you have a GCF that's out in front of the parentheses, which means that if I take this GCF and I distribute it back through, I should get back to the original problem. So I'm just going to check this last one here very quickly. I'm going to distribute the 6x squared y squared to 5xy, which gives me 30x cubed y cubed. And then the 6x squared y squared, I'm going to distribute over and multiply by the 1, which gives me 6x squared y squared. So I can tell that because when I distributed, I got back to the original problem that was given to me, I know that I've done this one right. So in this particular case, my final answer is right here, and I've actually gone through below it and done the check for that. So you always should get these right because you're factoring, and then you're going to distribute it back, and it's going to turn out to give you exactly what you started with. If you flip to the next page, on the next page we have some questions that are difference of two squares factoring, also known as dots. And dots only works if both of your terms, this 2 here means that you're going to have two terms, and if you look at every problem that's here, there's two terms. And what this means is both of your terms also have to be perfect squares. So the numbers that you get have to be numbers that you can take the square root of, and the variables must be even exponents. When you do difference of two squares factoring, it only works when you have a difference, which means you have to have a subtraction sign in each of the problems. And as you look at this, you can see that they do. The directions that we have at the top here say that we're going to make two parentheses that look identical except for the middle sign. I'm going to take this 4x squared and say the square root of 4 is 2. And put a 2 in both of the parentheses to start. The square root of x squared in the original problem is x, so I'm going to put an x in each of those problems. I'm sorry, in each of those parentheses. And then I'm going to do the same thing with the 9. The square root of the 9 that's here, if you want to write it that way to help yourself, feel free, is going to be 3, so I put a 3 in each of my parentheses. And the rule is you have 1 plus and 1 minus. 1 plus and 1 minus. The directions here do say that we can check this by doing FOIL. So if I wanted to check this, I could go through and FOIL the whole entire thing out. So I could multiply 2x times 2x, which gives me 4x squared, 2x times negative 3, which gives me negative 6x, 3 times 2x, which gives me plus 6x, and positive 3 times negative 3, which gives me negative 9. And when I do this, I notice that the outer and inner terms cancel out, which means that I end up with 4x squared minus 9 when I check, which is exactly the problem that we started with, which verifies to me that this is my final answer on how I factor, because when I FOILed it back, it ended up checking. So every single one of these kind of problems we do the same way. When I go to question 5, I'm going to acknowledge that it's dots because the numbers 149 are perfect squares and the exponents that I see are even. And there's two terms that are separated by a minus sign. That's the D in the word dots. That's a difference. I make two sets of parentheses. I square root what I have. Square root of 100, 10. Square root of x to the 8th is x to the 4th. 1 plus, 1 minus, square root of 49, 7. Square root of y to the 10th, y to the 5th. And that's going to be my final answer. I could, of course, check that by doing FOIL, but I'm not going to take the time to do that right now. When I go on to question 6, some kids will overlook the fact that this really is a dots question. You want to keep in mind that you're looking for two perfect squares, which I have because the exponents are even, and I should have a minus sign between my two terms. As soon as I acknowledge that it is a dots question, I make two sets of parentheses. The square root of y squared is y. That goes in both parentheses. The square root of z squared is z. That goes in both parentheses. 1 plus, 1 minus. And again, I could check that using FOIL. In number 7, it is also a dots question. You can square root 1. The square root of 1 is 1. In this particular problem, whatever starts the question, the original problem, is what has to start the parentheses. So because I have a 1 written first in the original problem, square root of 1 is 1, it's going to go in the first spot in the parentheses. You can see that the m squared ends the original problem, so it's going to be at the end of each of these two parentheses. Square root of m squared is m. 1 plus, 1 minus. And I could FOIL that back and prove that I do indeed have the correct answer when I factor it that way. Written below are 3 examples of questions that kids typically mistake as being dots questions that are not. So we're going to talk about why these 3 are not dots questions. In number 8, it is not a dots question because it's x to the first, and we would need it to be even. So I'm going to put a little note here that the exponent must be even. And in this case, it's not. In number 9, it is not a dots question because the plus sign that's in here doesn't follow the pattern for dots. According to the pattern for dots, the D that's there must be a difference. So we need our sign to be a negative or a subtraction sign. I'll write subtraction here. The sign must be subtraction, not addition. In question 10, as you look at this and you think about the dots, the D stands for difference. That's perfect. We have that. And then it's the difference of two squares. This is a perfect square because it's even, so that's good. We kind of check that off in our mind. But it says that there has to be two squares. And when I look at this, 2 is not a perfect square. So I need to make a little note here that the reason why this is not a dots problem is because the numbers used must be perfect squares. Which 2 is not. So 2 is not a perfect square, so this does not fit the way of factoring using dots. On the next page, you will see that you do have some example problems. And on this page, please do questions 11 through 14 by doing GCF. And please do questions 15 through 18 factoring using dots. And when you're done with those questions, you can go ahead and begin working on tonight's homework.